Gnanam paramam dhyayam. Knowledge is supreme.
Okay, so we have been debating on the concept algebraic and its minimal polynomial and so on. So let me formally define, suppose, so definition, K field, base field always, and a K algebra. We say that A is algebraic over K if every element x in A is algebraic over K. That means it satisfies a non-zero polynomial with coefficients in K. Then such an extension is called algebraic extension. For example, we have seen already finite dimensional algebras are always algebraic. If dimension of K as a vector space over K is finite, then A is algebraic over K. Particularly you can take A equal to, let us say, C and K equal to R. Then we know that dimension of C as a vector space over R is 2, which is finite. Therefore, every element Z in C is algebraic over K, algebraic over R, and it satisfies a polynomial of degree less equal to 2, because the dimension is at most 2. Minimal polynomial will be bounded by the dimension of the bigger algebra. So therefore it is either a linear polynomial or quadratic polynomial. So you know how to find that also. It is very easy to find that. So suppose Z is x plus iy, then you want to find this minimal polynomial of Z. So think of this x plus iy as x comma y, because we have identified C with this real vector space of dimension 2, and this is the isomorphism between them. 1 comma I is a basis, so that means this. So that means I want to find a minimal polynomial of this, which is like a particular case of the earlier example. That means that I will do it by finding the matrix of this multiplication, left multiplication by this element. So that means what matrix I want to find? That means I want to find, if I take a map from R2 to R2, this is a left multiplication by this x comma y. That means E1 goes to x E1 and E2 goes to y E2, and then the matrix is what? It's clear. The matrix is x here, y here, 0 here, 0 here. Then you have to find the minimal polynomial of this matrix. So and then you get back to the identification. So check that there is a little sloppiness in this, so which is better corrected like this. So, because we have identified, this identification is only identification as a vector space. It is not identification as a algebra. That is the sloppiness here. So, the best way to do is, so you want a real polynomial and degree is at most 2. So, obviously x minus z should be a factor and the other factor will be x minus z bar. This polynomial is x square minus z plus z bar x plus mod z square. This is a minimal polynomial. So, when this is 2 times real part of z, I think this we have argued earlier also, this is the x square plus y square, z square is mod z square is by definition x square plus y square. So, this is the minimal polynomial, it can't have satisfy smaller than that unless that z is already a real number, and in that case it will be linear polynomial. So, that is how one should try to calculate. Now, it becomes important to test, how do we test an element is algebraic or not in a simpler way. That means I want to bring in more theoretical consideration to decide. For example, before we don't have to check anything. If I give you finite dimensional algebra and say check that it is algebraic, you definitely know finite dimensional algebras are algebraic. So, now I am preparing to state the characterization of algebraic elements. So, remember the situation is like this: A is algebra and x was an element there which is algebraic. Then we have the subalgebra generated by x, that is kx, which was isomorphic as a k algebra. This is under that epsilon x. This is kx modulo mu x, ideal generated by mu x. So, x is algebraic, then this isomorphism. So, that means the degree of this is mu x. So, first thing to note here is, if A may not be a field. So, first thing to note is if suppose A is an integral domain, then this is a subring of, it is a subalgebra of this. So, in particular subring. So, then subring of an integral domain is integral domain. So, this kx is also an integral domain. That means this residue class algebra mod mu x is also integral domain, because these are isomorphic algebras. So, and so kx mod ideal generated by mu x is also integral domain. But that means this ideal is a prime ideal. So, that is the ideal mu x is a prime ideal. So, that then this mu x is a prime polynomial in the polynomial ring over K. Let me remind you, prime polynomial means a monic polynomial which is not a unit, and it cannot split into two proper factors. That means the only divisors are unit times that itself. Those are the prime polynomials. So, for example, in Rx we have seen what are the prime polynomials. If K were R, the prime polynomial examples are monic, I am writing monic. So, one is x minus c, these are linear ones, and the other one is x square plus bx plus c with the discriminant, that is b squared minus 4c negative. These are precisely the prime polynomials over Rx. Over Q there are many, in fact given any degree we have a prime polynomial and many. So, given any n, x power n minus p or x power n minus pq, all these are prime polynomials over Q. So, over Q the theory will become more difficult, over R it will be simpler, because an elements of C over R which can satisfy as a linear polynomial or quadratic polynomial with the discriminant negative. Okay, so now if it is an integral domain, let us take this case for, because ultimately we want to concentrate on algebras which are fields in fact. But if it is a field, then definitely mu x is prime polynomial, and then this kx is an integral domain definitely. Let us consider this case. In that case, I can talk about its quotient field. So, quotient field of this integral domain is usually denoted by k round bracket x. That means what? And why do I denote it by this notation? This means they are rational functions in x, but they should make sense. So, that means what? They are fractions fx mod gx divided by gx, but then this should make sense. So, f and g are two polynomials in k, and the g cannot vanish at x. In particular, g is not 0. So, take those fractions, and that will form obviously a subfield. If A were a field, so we are assuming here now that A is a field, or not necessarily a field, but then this may not be contained in K. Definitely this makes sense, but it may not be contained in K. In case when A is a field, actually this is the smallest subfield of A which this integral domain is contained in. So, I hope you have seen the general construction of an quotient field of an integral domain from an integral domain. So, that is the similar way we have seen in the school already, that how do you construct Q from Z. This Q is a quotient field of Z. This is QTZ. I will denote standard notation, I will denote this QT means the quotient field. So, you take the integers and take their fractions A by B, where A, B are integers and B is non-zero. Such fractions is form a field, and it is the smallest field that Z can contain. Similarly for this. So, therefore, this Kx is smallest field which contain this Kx. And remember, there is no special that this x is one element. I could have done it for bunch of elements. Namely, I take the subalgebra generated by that, and if that subalgebra is the integral domain, I will embed in a smallest quotient field, and that is what the construction I am talking about. If I have arbitrary elements x1 to xn, and I consider the subalgebra generated by them. Subalgebra generated by them means the smallest subalgebra of A which contain all these cases. This is the smallest K subalgebra of A containing all these guys x1 to xn. So, if this is an integral domain, I talk about the quotient field, and then I use the notation k round bracket x. So, this is precisely what I kept saying in the earlier lecture, that given a field I want to adjoin some element and make it a bigger field. This is for example, it is a bigger field now. I have adjoined that x to the field. Similarly, here not I have adjoined one element, but many elements. So, I will digress on these more elements more. Right now, I concentrate only on one element and state our theorem which characterizes algebraic elements. So, this is the theorem I am interested in proving. So, theorem. As usual, K is a field, A is a K algebra, and X is an element in K, element in A. And we want to know when this element is algebraic. So, I am going to state equivalent conditions, one of them will be algebraic. Okay. Then, and I will use this abbreviation all the time in the course, the following are equivalent. So, this is the abbreviation for the following are equivalent. This is throughout the lecture. Throughout my life, I have used this because of my teacher. Okay, so, 1, the K, the subalgebra, the K subalgebra Kx. This is a subalgebra of K generated by X is a field. Remember, what do we know? This is a subalgebra and all elements are precisely the polynomials evaluated at that x. And the condition 1 says it is already a field. 2, x is algebraic over K, and the minimal polynomial mu x of x over K is a prime polynomial. In Kx. So, you see, if you want to test somebody's algebraic, you just have to check that the subalgebra is a field. So, it's an integral domain. It may not be integral domain. It is a part of that. It is an integral domain and it is a field. Okay. So, let us check that. Remember, I am not assuming A is a field. I am assuming A is only a K algebra. This is only a K algebra. So, and this K subalgebra is a field, that is equivalent to saying X is algebraic. So, let us prove this. So, proof. So, it gives the fieldness of this K subalgebra not only gives information that X is algebraic, but it also gives the information about the minimal polynomial, that it is a prime polynomial. All right. So, 1 implies 2. So, I have given that subalgebra is a field given Kx, which is a field. Remember, this is isomorphic as a K algebra to K polynomial x modulo ideal generated by the minimal monic polynomial of x. This we know, this is by definition. This is a K algebra isomorphism. All right. So, this we know. Okay, so the first thing I want to note is this mu x has to be, we have given this subalgebra is a field. Then I want to prove that, so this is just for recalling. What do you want to prove? We have given this, so given Kx is a field. Then from this isomorphism, you conclude the mu has to be non-zero. Then mu x has to be non-zero. Because if mu is 0, then this but this Kx is not a field. K polynomial x is never a field. So mu x is non-zero. But that already means that x is algebraic. Because algebraic means it should satisfy a non-zero polynomial, and this is the minimal polynomial. This is non-zero means, and x satisfies that means the kernel is non-zero. Therefore, x is algebraic. Also, now I want to prove that it is a prime polynomial. But if it is, so if suppose mu x splits into two factors f times g, then what do we know? Then mu x evaluated at x is 0, that is by definition of mu. So this will be f times g evaluated at x, but this is because it is algebra homomorphism, evaluation is an algebra homomorphism. So this is fx times gx. And where are these elements? These elements are in K small x. This is this, but this is given to be a field. And this product is 0 in a field. Therefore, each one of them be 0. So that will imply fx is 0, and also gx is 0. No, fx is 0 or gx is 0. But fx is 0 will mean that, so that will mean that f, so that will mean that f belong to ideal generated by mu x, or g belongs to the ideal generated by mu x. In particular, the degree of f will be bigger equal to degree of mu, or degree of g will be bigger equal to degree of mu. But f and g were factors, they were proper factors of mu. So this is strictly less than degree mu. This is also strictly less than degree mu, a contradiction. Either this or this is a contradiction. A contradiction. So that proves that if K small x is a field, then x must be algebraic and the minimal polynomial should be prime polynomial. Now conversely, that is 2 implies 1. We have given what did we give? What we have given? We have given that mu x, which is a polynomial in Kx, minimal polynomial. This is monic. It's a prime polynomial. And x is given to be algebraic. So that means this mu x is non-zero given. Because kernel is non-zero, generator has to be non-zero. So, and it is given to be prime polynomial, and I want to prove that Kx is a field. But that is also obvious, because what do we know? We know that Kx mod mu x, this is isomorphic as K algebras to K square bracket x. And we want to prove this is a field. but I have given this is prime polynomial, so it generates a prime ideal. So mu x, this is a prime ideal in Kx and non-zero prime ideal because mu is non-zero. Therefore, now I want to use the fact that Kx is a principal ideal domain in that every non-zero prime ideal is maximal. Once I know that, this mu x will be a maximal ideal and residue class ring of a maximal ideal will be a field, and therefore this will be a field. So enough to note that you have learnt in earlier course. So enough to note that every non-zero prime ideal in a PID, PID stands for principal ideal domain, is maximal. I will not prove this, but I strongly recommend that you should check this on your own by recalling whatever you have learned in the first course on algebra, namely rings, fields and groups, rings, fields. But this I can also digress in a little bit simpler way, but you will have to use same technique to prove that every non-zero prime ideal in a PID is maximal. So what do you want to prove? I want to prove this is a field. So I will indicate for you that this is a field without using this. This is a field. You want to check that. Alright. So that means what? I have given any element here non-zero, 0 not equal to any element will look like f evaluated at x, where f is a polynomial in coefficients in k. I want to produce a inverse for this f. This means what? This means this f cannot belong to ideal generated by mu x, because mu x, this ideal precisely all those polynomials which vanish on x. So this is not there. That means this, and we know we have also given that this mu is a prime polynomial. Mu x is a prime polynomial. So that means mu x cannot, so this means mu x does not divide f in Kx. This is a prime polynomial and this does not divide this, so their GCD should be 1. So this means GCD of mu x and f is 1. But remember, like integers, GCD of two polynomials over a field is 1, then 1 is a linear combination of the two. So that will imply I can write 1 as what do I have notation? S times mu x plus t times f with s and t, two polynomials with coefficients in k. This is known as Bethe lemma. This is what is true for integers, and the same proof for polynomials as do it for integers, because we know this polynomial ring has a factorization and the division algorithm that use the same thing. Now once we have this, now evaluate this. This is a polynomial identity. Evaluate this at small x. So that will imply 1 evaluated at x is 1 only, s evaluated at x, mu x evaluated at x plus t evaluated at x times f evaluated at x. But mu x is 0 because mu is a minimal polynomial of x. So this term goes. So 1 is equal to tx times fx. So this tx is the inverse of fx. So assuming fx is non-zero, I have proved that it has the inverse, and this inverse belongs to k small x. That means I have proved that this Kx is a field. That is what the condition we wanted to prove, which is 1. That is 1 satisfied. So, this is in some sense less technical, but and also it gives you actually, this method actually gives you how to produce inverse of f, but sooner or later we have to go and use high powered machinery which will have vocabulary from what is called commutative algebra. Commutative algebra means prime ideals, maximum ideals and so on. So, time to time I can give simpler proofs and also use some new definitions to give a little bit proofs which involve more concepts. That way one can learn more concepts easily through these examples. So, I will stop here and we will continue about algebraic extension next time. Next time I am going to attach a group to an algebraic extension and what will be called a Galois group, and we will study the algebraic extension using this group, and that interplay I will become I will make it more and more intimater. So, I stop here till next time. Thank you.